In this video we will be discussing atomic structure and electron configuration. And to start off with the story behind how we came to our current understanding of atomic structure is very interesting. There's a lot of inspiration and motivation in this history. Unfortunately, due to the nature of this video series, we're mostly focusing on addressing how to approach chemistry-based problems. We won't be going into that history very much. We'll just launch off directly from modern atomic theory. But if you have time, I do encourage you to go and have a look, because it was very interesting to see how it progressed and how the idea of the atom has evolved over time. But anyways, on to atomic theory, modern atomic theory. The basis of modern atomic theory is that there's 3 subatomic particles, which make up all atoms that we are made up of, that we encounter as we go through chemistry. And so these 3 particles are shown here in this little drawing of the atom. You have red dots being protons. And these protons have a positive charge, and they're found in the nucleus, and they tend to be quite heavy. Next, you have the neutrons. As their name suggests, they're neutral, and they're also found in the nucleus, and they also are quite heavy. And then finally, we have electrons. And these electrons have the same amount of charge as protons. They're just negatively charged, and you don't find them in the nucleus. You find them around the nucleus in something called the electron cloud. And so when we look at this, you'll see that there's a very dense nucleus where you have the protons and neutrons jam-packed together. And then out here, you have a bunch of electrons kind of taking up the rest of the space. And so when we look at atoms, according to modern atomic theory, we see that they're mostly empty space. You have this dense nucleus, and then the rest of it is kind of loosely filled with electrons which are orbiting around the nucleus. So that's all very nice and good, but now we want to figure out how these subatomic particles allow us to convey properties of the chemicals or molecules that we're working with. And the way we'll do this is we'll use 3 numbers. The first one will be our atomic number, which is characteristic of each element. Then we'll have something called a mass number, and then we'll finally round things off with the charge. So to start off with a familiar example, maybe we'll go ahead and look at carbon. So within carbon, our atomic number is going to be 6. And what this is telling us is that within the carbon atom, we have 6 protons. So this here, the atomic number, tells us the number of protons. So if something has more than 6 protons, say 7 protons, then we know it's not a carbon atom, it must be some other atom. In the case of 7, it'd be nitrogen. Similarly, if there was 5 protons, we'd know it'd be boron instead of carbon. Okay, so that's the atomic number. And then up here, what we'll have is something called the mass number. Then I'm going to abbreviate protons as P and neutrons as N. And as we go on later, I'll abbreviate electrons as E. So number of protons plus number of neutrons. So what does this mass number tell us? One thing is, you'll notice that the mass number is only equal to the protons plus the neutrons. The reason this is because electrons, even though there's the same number of electrons as protons in a neutral atom, the electrons weigh basically nothing. The mass of a proton is similar to the mass of a neutron, but both of these are much, much larger than the mass of an electron. It's similar to, say, Pluto orbiting the sun. Right? The sun is so massive that barely recognizes that Pluto's out there orbiting it. Similar thing here, where the protons and neutrons are so massive that changing the number of electrons doesn't change the overall mass of the atom. So that's the mass number. And then finally, we have up here the charge. So if you don't see a number there, the charge is 0. What that means is that there's an equal number of protons and neutrons. But you could have a charge on carbon, say, +2. And we'll go into a little bit where we get that. So going in order, atomic number, if you change the number, you change the element. Not much to it. But what about the mass number? So you see here we have 12. What if we had carbon 14, right? So they both have 6 protons, so we both know they're carbons. But carbon 12 is different than carbon 14 because carbon 14 has more neutrons and it weighs more. So the number of neutrons in both of these is going to be mass number minus the number of protons. So here it's going to be 12 minus 6, gives us 6 neutrons. Similarly over here, we can do the same thing, but it's going to be 14 minus 6. And so these two are called isotopes of carbon. And an isotope just tells you that they have different numbers of neutrons, but they must have the same number of protons, otherwise they'd be different elements entirely. So an isotope just tells us that there's different number of neutrons. Okay, so let's go back to charge. How do we get the plus 2? Well, if we say carbon has 6 protons, but as shown here we have 6 electrons initially, but if we then erase 2 of the electrons, suddenly we only have 4, so we're going to subtract 4 electrons. And so we end up saying that we're going to have a charge of plus 2. Your charge goes there, showing that you can calculate the number of electrons from the charge, right? You take the number of protons, and if this is a negative number, you add the two together to get the number of electrons. If it's a positive number, you subtract it. So another way to think about it is atomic number minus charge equals the number of electrons. Okay? So let's go ahead and do another example where we're going to wrap all this together. Let's say that we have oxygen. So we have oxygen 16, as you may know, or you can look at your periodic table, the atomic number is 8. Let's say that has a charge of minus 2. Okay, so we come here, number of protons is going to equal 8. Number of neutrons is going to equal top number minus bottom number. Going to give us 8 as well. And the number of electrons is going to equal atomic number minus our charge, which is a negative 2. It tells us that there's 10 electrons on this particular oxygen. Now you'll notice that since this is 2 minus, it's no longer just an atom, it's what we call an ion. So an ion just tells us that there's some charge here. And if it's positive, it's going to be a cation. And if this is negative, like it is here for oxygen, it's going to be what we call an anion. Okay, good. So going off of what we've learned here about electrons, we want to build upon our understanding of electrons to be able to tell each other where they are. And the reason this is important is because the properties of our molecules or of our atoms will depend heavily on what are called valence electrons. So if we look at our carbon atom here, we have 2 rings. These rings represent principal energy layers. So this would be the first principal energy layer, has the lowest energy, it's closest to the nucleus. This would be the second. And you see that the first one has 2 electrons in it, and the second one has 4. So these 2 electrons fill this layer here, this first energy level, and then these 4 don't quite fill the second. When we're looking at principal energy levels, let's say we have energy level 1, 2, 3. The number of electrons, so this is the energy level. Number of electrons is going to go 2 for the first, then 8 for the second, and 8 for the third. And so we see that this one is not full, it only has 4. So those are what we call valence electrons. Those are the ones that really interact with the matter around this atom. These 2 electrons closer to the nucleus are what we call core electrons. They're shielded from interactions with the surrounding by these valence electrons. They don't do much. They just kind of sit close to the nucleus and enjoy their positioning. Okay? And so, as we're conveying information about electrons, we want to be able to convey where they're at. Right? It's very similar to if you're sending a letter to someone. You need to know what state they're in, what city, what street it's on, and then what number on the street it is. Similarly, with electrons, we need to know more information than just these primary energy levels. And so how we do that is we're going to have an energy level. This is always a number. And we're just going to go 1, 2, 3, and 4. Okay? Within each energy level, we're going to have a sub-energy level. Or we'll just call it a sub-level. So we can have as many sub-levels as the number of the energy levels. So here, we're just going to have 1. Here, we're going to have sub-level 1 and sub-level 2. Here, we're going to have sub-level 1, 2, and 3. And then finally, here we're going to have sublevels 1, 2, 3, and 4. Okay, so these sublevels are going to be assigned letters as we continue on. So this one's going to be S. All the ones are going to be S. And then 2s are going to be known as P sublevels. And then the 3s are going to be known as D sublevels. And then finally, the 4s are going to be F sublevels. So a good way to think about it, this is your state, this is your city. Okay? So once we know sublevels, then we can do orbitals. And this tells us how many orbitals are in each sublevel. So that's like saying how many streets are in a city. Similar concept. So in sublevel S, there's only 1 street in the city. It's a very, very small city. It's more of a town. So there's going to be 1 orbital. Similarly, for energy level 2, because you have sublevel 1, that one will have 1 orbital. But then sublevel 2, because it's a P, will have 3. And so as you increase in sublevel, the number of orbitals increases to the next odd number. So here it's going to be 1 again, 3 again, and then since this is a 3, you're going to have 5 orbitals. Same thing here. You're going to have 1 orbital, 3, 5, and then 7. And there's a very good reason why this is. It's due to a principle which we'll discuss later called the Pauli exclusion principle. But we won't go too much more into that. This is what's important to know. Okay. And then finally, you also have something called the spin. And so if you go back to thinking about planets, the Earth orbits around the sun, but then while it's orbiting around the sun, it's rotating about its own axis. Similar thing with these electrons is that while they're orbiting the nucleus, they can spin around their own axis. And so there's 2 ways you can identify them. You can do clockwise, counterclockwise. I prefer to use up and down, but that's going to be true. And the reason I prefer up and down will kind of become clear in a second. But this is going to be true for all the orbitals. So all of them have the potential to be an up or a down. Okay. Good. So what we're going to use this for is we're going to use this to draw orbital diagrams and write out what's called an electron configuration, which is essentially a short form of an orbital diagram. And as we're about to move on, I want you to keep in mind that as you increase in the number of sublevel, your energy gets higher as well. So here, this 4s orbital, this 4s sublevel, has a lower energy than the 4p sublevel, has a lower energy than the 4d sublevel, which has a lower energy than the 4f. So it increases as you go down. Okay. So we'll go ahead and erase that.